Today we will be discussing the idea of solubility. Solubility is a measure of the amount of something that can be dissolved per volume of solvent. The way to think about this is just how much of something can dissolve depends on how much water you got. If you're using water, I can dissolve more salt in something the size of the ocean than I could in a cup or into my bathtub. So imagine that you have 2 volumes of liquid. We'll just use water as our example. I might be able to put an amount of salt into here that would completely dissolve, but then maybe a similar amount of salt wouldn't dissolve over here because there wouldn't be enough water. Or another way to think about it is I can keep adding some ionic solid into this vessel, and it would dissociate, it would break up, and it would break up, and it would break up until it became saturated, and then no more would break up. And the same here. Now the amounts would be different, but if we're dealing with the same ionic solid in each flask, then the amount per liter should be the same if we're dealing with the same thing. So bigger flask might dissolve more absolute amount, but per unit volume they should be the same for the same substance, assuming that the thing can dissolve at all. A lot of times we talk about insoluble substances. Oh, I skipped a page. So anyhow, whenever we measure amounts can be in grams or they can be in moles. So usually if we're just talking about solubility, we mean grams per liter. If I ask you what the solubility of something is, the answer would be in grams per liter. Or there's the molar solubility, which would be the same number, the same amount, but it would be expressed in moles per liter. So be ready to get whichever of those they're asking. So a lot of times when we talk about ionic solids being insoluble, we don't really mean they're insoluble. What we mean is that they're really bad at dissolving. They're really bad at dissolving. They don't dissolve very much. They do dissolve, but not very much. And so this entire lesson deals with how we can calculate the solubility of things that don't dissolve very much. So our example that we're going to use is iron 2 hydroxide, also known as ferrous hydroxide. So here we have the solid. We're going to start by writing a solubility reaction showing the dissociation of these ions in water. So this doesn't happen very much, and what does happen often reprecipitates as a solid, so it is going to be an equilibrium situation. So we are going to dissolve into these ions. Well, the ions are iron, obviously. And we're going to now write that as aqueous, not as a solid anymore because it's dissolved. And we're going to make hydroxide ion, which is also aqueous. However, you'll notice that for every 1 iron that dissolves, you're going to dissociate 2 hydroxide. So this subscript here shows up as a coefficient on the other side of the equation, and there is our solubility reaction. Now, introducing the solubility product constant. For this particular compound, iron 2 hydroxide, there exists a constant called the solubility product constant, abbreviated KSP, the SP for solubility product. And that number it's a K value. This is an equilibrium. We can write an equilibrium expression, and we can say that this K value is true for iron 2 hydroxide. Now, you can get this out of a book. You can Google it off the internet. K values for salts, for ionic compounds, are known. So if you're working out a problem, often it will give you the K value and ask you for the solubility. It can be done, though. It could go the other way. And so in this problem, we're going to use the solubility product constant to calculate both the molar and the mass solubility of the iron 2 hydroxide. So what's that going to look like? Well, we're going to start by writing a K expression. We're going to write a K expression the way we always would. So KSP is going to be equal to the products equilibrium concentration of iron 2 times the equilibrium concentration of hydroxide. But that's got to be squared because of the coefficient 2 there. So that oh wait, it's not over anything, it's over 1 because that original iron hydroxide is solid, so it's not going to participate in the equilibrium. So we're done. That is our equilibrium expression. So what we can do is we can use this to go ahead and solve the problem. So what's that going to look like? So here's our K expression. But problem is we have two variables here. We have two variables, only one equation. K is known, it's that number that I had on the other sheet, 7.9 times 10 to the negative 16th. And we're going to needs to come up with a relationship between the iron and the hydroxide so that we can solve this. So we don't really know anything. All we know is that some amount of this stuff dissolves, so we don't know how much is going to dissolve, so let's just call that number X. So if X iron ion dissolves, then it's also true, I think you'll agree, that twice as much, or 2X, hydroxide ion dissociates. And now we pretty much are done. We have everything we need. We have one variable, X. We can plug this into the expression. We have the K value from the previous sheet. So K is 7.9 times 10 to the negative 16th. And that equals iron, which is X, times hydroxide, which is, careful now, 2X, quantity squared. A lot of times, for some reason, kids don't want to do the 2x and the squared. They think, oh, well, we've already doubled it, we're not going to square it. No, both the coefficient becomes 2 and the exponent becomes 2. So now we're going to simplify this. For 2x quantity squared is not 2x squared, it's 4x squared. And then we're going to take that times x, which leads us to 4x cubed is going to equal this K value. So now we're going to divide both sides by 4 to get x cubed alone. And so 7.9 times 10 to the negative 16th. We're going to divide that number by 4. Is 1.975 times 10 to the negative 16th. And then that's going to equal x cubed. Getting kind of messy here. So we need to take a cubed root there. So fortunately I have a cubed root button, so this will be quick and easy. So x now is 5.8 times 10 to the negative 6th. So what that means is that exactly what it says. X is 5.8 times 10 to the negative 6. What's x? X is the iron concentration at equilibrium. So we would say that the iron has a solubility of the iron ion at equilibrium will have a concentration of 5.8 times 10 to the negative 6th. And the hydroxide ion concentration is going to be not x, but 2x, not 2x squared either. Remember, this isn't the concentration of the hydroxide. This is how you calculate the K expression. The hydroxide concentration is just 2x. The iron concentration is x. So we're going to take 5.8 times 10 to the negative 6, and we're going to double it to get our hydroxide concentration of 1.16 times 10 to the negative 5th. And the units here are molars. When you use a solubility product constants to get a number, you found the molarity, the molar solubility. So if this was asking the molar solubility, it's actually asking for the molar solubility of this stuff. So we need to find the thing with the same coefficient as this, which is here. So that number x is the answer here. So the molar solubility of iron 2 hydroxide is that 5.8 times 10 to the negative 6th number. Now there's one other thing that we could be asked to do. We could be asked to find the mass solubility And the nice thing here is this isn't a complicated question because we already got the molar solubility. If you have molar solubility, you can multiply that by grams per mole to get grams per liter. Well, what's grams per mole? Well, that's just the molar mass. So we know from the last sheet that the molar solubility is 5.8 times 10 to the negative sixth for iron 2 hydroxide. And so we can just multiply that by the molar mass of iron 2 hydroxide. Ooh, oh goodness. I forgot to work this out before. I hope iron has a molar mass of 5.8. And times 30, add 34. Woo! That's 17 and 17, so 89.8. I'm close. So we're going to take that times 5.8 times 10 to the negative 6 to get 5.2 times 10 to the grams per liter. So this is the solubility of iron 2 hydroxide, and this is the molar solubility. Then you could have questions like how many grams can dissolve in 12 liters. Well, it's just going to be this times 12. So that's kind of how you do a problem like that. You could also work a problem the opposite way. We're not going to do it right here, but you could go the other way where you start with the solubility and need to calculate a K. And so that's just a matter of taking the solubility, making sure it's in molars, writing your K expression, and plugging those numbers in.